Okay, so let's suppose that the car goes a distance of 6 feet. Okay, so the car travels 6 feet and then stops in this circle counterclockwise to 3 o'clock. How many radians of angle measure did the car sweep counterclockwise? How many radians of angle measure? Everyone think for yourself. Let's see how we're doing on this stuff. So can you give me, so no calculators. We're going to write everything as expressions, right? So we're going to express everything exactly, and we're not going to do any punching and getting approximations. Okay, so can you express exactly how many radians of angle measure the car went through an arc of 6 feet? So let's see if you can do that. How about... Oh, Sayla wants to try. Okay, go ahead.
First step is we get theta, and they refer to that to radians.
No, I'm asking what the measure of theta is. I'm asking what the measure of theta is.
6 over 8.
Okay, he wants that angle would be 6 over 8.5. Agree or
Times pi over 180.
times pi over 180. So we want to know what angle measure in radius length, in radians, has the car swept? So somebody new. Marquise, what do you think? She wants 6 over 8.5. Angelica likes that. Yeah, because what's equivalent to the radius length, or what's equivalent to the angle measure in radians? Where does that number come from? That angle measure in radians? Number of radius lengths swept on the arc. So the car has gone 6 of 8.5 radius lengths on the arc, so that becomes also the angle measure in radians. That's where radians comes from. How many radius lengths of arc length is cut off by the rays of the angle? Okay, so what about then how many radius lengths, or what fraction of a radius now is the car above the horizontal diameter? Can you express what fraction of a radius the car is now above? So no calculator, just we want to express it. So again, what fraction of the radius is the car above the horizontal diameter? So what do we think here? Yeah?
Times 6 over 8.
What is it?
Sine 6 over 8.
Okay, it's not times, it's a function, right? Acting on. So sine of 6 over 8.5. Agree with that? Right, so sine gives us, I was asking you for vertical distance as a fraction of the radius. That's what sine is, vertical distance. So we just need, so then it's going to be sine of 6 over 8.5. Okay, how many feet? Okay, how can we express how many feet the car is now above the horizontal diameter? No calculator, we want to express it as a number of feet. Yeah, Elise. Right, so if this is the fraction of a radius length, then we're going to take that fraction of 8.5. We're going to take that fraction of 8.5. This should make sense. So that's feet. Okay, what fraction of a radius length is the car to the right of the vertical diameter? Try somebody new. How about Adam? What fraction of a radius length is the car to the right of the vertical diameter? How could you express that? Not sure. Okay. Scott?
It would do the same thing, but you would cosine.
Cosine of the angle swept by the car. So he wants cosine of 6 over 8.5. So let's kind of label these here. So this right here, this was our sine of 6 over 8.5 as a fraction of the radius, and then as it's the same measurement, but then in feet if you multiply by 8.5. So if you're measuring in feet, so according to in the picture, right? In the picture I'm showing this is 8.5 feet. So technically, that distance right there is this one, right? Because I'm showing this is 8.5 feet from there to there. But if I showed this was 1 as one radius length, then that distance would be this one, that fraction of 1, right? That fraction of the radius length. Okay, so then what is this cosine of 6 over 8.5? That's like this right here. It's the car's horizontal distance to the right of the vertical diameter. And then is that in feet or as a fraction of the radius right there? Fraction of the radius. So what would it be in feet? Flora? Yeah, we're going to take, so we want that fraction of one radius. 8.5 times that then takes that fraction of 8.5, and we get that dimension in feet now. Feet. Okay, so let's put these expressions in our calculators and see if the numbers make sense now. All right, so make sure your calculator is set to radians, and let's enter in this one. Or let's predict first. So before you punch, let's predict. So in feet, how many feet above the horizontal diameter do you predict the car is right now? What would you predict based on the picture? How many feet? How many feet up would you estimate the car to be right now?
6.6.
No, in feet. In feet. Okay, to me it looks like a little bit more than halfway. Would you agree? What's half of 8.5? 4.25. So a little bit more than half of 4.25 would be around 4.5 or 5. 4.5 or 5 feet. Does that make sense? I didn't hear a lot of good estimates coming up. Right? So a little bit more than halfway up. So maybe 4.5. And now let's estimate this. So again, don't punch. How many feet to the right of the vertical diameter would you estimate the car is at this moment? How would you estimate by looking at there? All right, now we're talking about 7 or 8, right? 7, close to 8.5 now, maybe 7, 7.5 feet. So now let's find these values. So we estimated about 5 feet. And then someone said 7. I think that's decent. So something like that. So that's what we're thinking. So do 8.5 sine of 6 over 8.5. And what do you get? 5.5. Okay? 5.5 feet. And that makes sense. 5.5 feet up. And then what about 8.5 cosine of 6 over 8.5?
6.5.
6.5. There you go. So we got 7. Okay. So is it making sense what the meanings of sine and cosine are, and how then it can be used, applied to any circle, right? Since it's a fraction of the radius length, then if you know the radius of any circle, you can just apply those fractions to the radius length, and you get the right distances, right? Distances in this case, feet. So let's do some more practice of this. So I got a similar situation here. I don't think we didn't start this on Tuesday, did we? No. Okay. So we got here's a track, right? And we got a runner starting at the start line here. And so the runner runs in a circular half circle. It's like a circular arc for a half a circle. Okay. And the radius is 36.5 meters to the inside lane. Okay. So now I'm showing that the runner has run 22 meters. So now no calculator for A through C. No calculator. You're going to express the corresponding angle swept by the runner in radians, and then express the vertical distance as a fraction of the radius length, and in meters, and then express the horizontal distance as a fraction of the radius length in meters. Okay, so just do A through C, no calculator. You're expressing them using what we've learned. And then you can compare with each other. Okay, you can work together and compare your answers. A through C. Okay, so you're expressing these exactly, all right? So you're writing expressions that give the answers exactly, A through C. A through C, and you're going to exact answers. Got some leftover quizzes to return. Christian, Mohammed, Khalid. Good. Marcelo.
Okay, you're just finding the fraction of rate. Yes.
Okay, then once you're confident about A through C, then you can get out your calculator and check them. Okay. See if so. Look at the values and then see if they make sense. Okay, so when you're checking them, those final values, do they make sense? Oh. My computer is not happy. Look at that. That's about it. There we go. Let's try it again. Okay, we're back. 22. So, angle is, let's see here. How about Adam? Did you get the angle? 5? Why 5 over 36.5? Where'd the 5 come from? You're just guessing. Okay, how do we find out what the angle in radians is? The angle measure in radians is the same as what? What's the angle measure in radians the same as? Where does that number come from when we measure an angle in radians? Yeah. So if you ran 22 meters and one radius length is 36.5, how would you get how many radius lengths that is? Jordan, what do you think? If you ran 22 meters, the radius is 36.5, and he ran 22 meters, and we're trying to figure out how many radius lengths he's ran around the arc of the circle, because that'll be the same as the angle measure in radians. Yes, you would. So hopefully, you got to have this stuff, the easy stuff down, right? So everything builds, as we've seen in past modules, everything keeps building on what we've done before. So don't forget the stuff, all this angle stuff that you just worked on in your quiz when we started module 7, because we're going to need it. Okay? So we want to express the vertical distance above the horizontal diameter right there as a fraction of the radius. You can do that. Naisha, did you get that? You did with what? Okay, so if I'm talking about the vertical distance above the horizontal diameter, then what am I talking about? That should be like light bulb. What is that? Vertical distance above the horizontal diameter. What is that? Naisha? That's sine. So what's the input into sine? What do we put into sine? That's why we memorize. That's why we're memorizing things, so we can apply all these meanings of the input and output. What is it that we put into sine? 36.5. Daniel, do you agree with that? What is the input into sine? Because what is the input into sine in general? Measure of the angle, what? So counterclockwise from 3 o'clock. In any, so you can use any, we're using radians, but you can do any angle measure for the angle, but we're doing radians. So here's the input. It's going to be an angle measure. Okay? It's going to be, and this is going to be what angle was swept by the runner. So 22 over 36.5. And does that give meters or something else? Fraction of the radius. Estimate it. So estimate it. What would you estimate the value of sine of 22 over 36.5 is based on where the runner is? What would you estimate it to be? Someone said 0.5. Good estimate? Yeah, it's pretty good. Maybe a little bit more. So 0.5 or a little bit more. Good estimate. Okay? How far, what fraction of the radius are we above the horizontal diameter? That's what sine is. Okay? How would we get that in meters then? Now we have that fraction of a radius. The radius length is 36.5. Now we want how many meters up we are. Justin? Yeah, we're going to take that fraction of 36.5. So we'll take that times 36.5. So you usually put the 36.5 in front. But we want to take that fraction of 36.5, and then we get how many meters above? something a little more than half, right? So 18, about 18 meters is half. Maybe this is 20, 22 meters or something like that. A little more than halfway. Did anybody do that? Did you put in, so in meters, how many meters? So what's 36.5 times sine? 20.7? Yeah, a little bit more than halfway. That's what we said. A little bit more than halfway up. Okay, express the horizontal distance to the right as a fraction of the radius length. Let's see. Chris? Cosine gives that, right? Cosine of what? Yeah. And now if we want that distance in meters instead of a fraction of the radius, so what are we talking about there? We're talking about from here to here. Yeah, we want that fraction. If we want meters now, we take that fraction, cosine 22 over 36.5 of, we take that fraction of the whole radius, 36.5. Should make sense. Again, usually we put the 36.5 in front, okay? But I kind of like it this way because then we think of, we're taking this fraction. So what would you estimate that fraction to be? What would you estimate that cosine to be? For right here. What fraction of a radius length are we to the right now? No, what fraction of the radius length? I'm not asking for meters. This is one radius length. What fraction of a radius length? Meaning just the cosine part. 0.8, something like that. 0.7, 0.75, 0.8, 0.85, somewhere in there. And then we were going to take that fraction of 36.5. And when you put it in your calculator, what do you got? 30.1 meters. Makes sense, right? It makes sense because we're almost all the way over at this point. So horizontally, the runner is still pretty close to the starting point. Still hasn't made much progress to the left. So 30.1 meters now from the vertical diameter. Okay, does it make sense? Let's see what else I got down here. Any questions? Anybody have a question? Okay, let's try it again for, so I want you to just do this. If the runner goes 59 meters, I want you to write the coordinates of the position of the runner in meters. Write the coordinates, okay? So no calculator. Position of the runner as an x and y coordinate in meters. Go, everyone do it. If the runner went 59 meters. And I'll show that. There's 59 meters, okay? So find the position as coordinates, x and y coordinates, in the unit of meters. Write it down. Express it exactly. In meters. So I want the coordinates in meters. Okay, so Araceli, you're up. How'd you do? What's the x coordinate of the runner in meters? So what's the x coordinate? How would you express the x coordinate of the runner in meters? Any idea? Drawing a blank. Is it Cassidy? Yeah. Did you get it? X coordinate of the runner in meters. No, I want exact. No calculator. I want an expression that's exact. 36.5 cosine of what divided by? How'd she do? Nailed it. Okay. 30. What's the 59 over 36.5? What does that represent? No, just the 59 over 36.5. Measure the angle. That's the angle, right? That's the input into cosine. It's going to be that angle measure, which is the same as how many radius lengths the runner has run, right? That's how many radius lengths the runner has run. Something close to 2, maybe. Okay? And then when we put that into cosine, what do we get? We get the horizontal distance as a fraction of the radius length. And if we want it in meters, we take that fraction of 36.5. So we multiply. Okay? So what's the y-coordinate? That should be easy now. So, yeah. Marina.
36.5 sine 59 divided by.
So make sure you're really confident about what every part of the expression means. So what does that ratio mean? Well, that's the input into sine or cosine. So that's how many radians has been swept out. Radians of an angle measure. What's just the sine or just the cosine? Well, what's the unit of measure when you just have sine or just have cosine? What's the unit of measure? Not radians. Fraction of radius length. It's a fraction of the radius length. Sine and cosine. And then you take that fraction of your radius and you get, in this case, you get meters. Okay? Anyone put in your calculator? What'd you get for the x-coordinate? Negative. Is that right? I think it's more than that. Negative 1.7? Oh. Well, according to the picture, that would be more than. It'd be more like negative 10 or something. No, everyone got that? Okay. All right, and then something's up. But so then what about for sine? It's going to be almost right. It's going to be almost 36.5. 36.46. Just, okay, so yeah, so it still should look better than that. Anyway, so just a little bit past the top is this number of radians. And so just barely past the halfway point would be 1.7 meters to the left and 36.2, did you say? Or 4? 36.46, just barely came down a little bit from the meters. So those numbers make sense, okay? Just a little bit to the left, and then hardly any down from the full 36.5 at all. Okay. Anybody have a question on applying sine and cosine? So knowing what every part of the expression means, and then being able to generate the expressions yourself. This is really important. It shows that you understand what sine and cosine are. Okay, so let's change gears here and let's look at our universal circle here, which we call the unit circle. It's our universal circle. Okay, it all started by looking at a radius. And doing what? Taking that radius and peeling it off and laying it on the circle. That's where this whole thing started, okay? And we said that corresponding measure of the angle was what? For one radius wrapped on the circle, we get an angle. What is the measure of that angle? Javier? 1 radian. Good. 1 radian. 1 radius length on the arc. This corresponds to an angle measure of 1 radian. And then from that, we marched around the circle, and we marked off one radius length at a time. So this would be 1 radian, 2 radians, 3, 4, 5, 6, and then all the way around. Do those fall? So when we do whole numbers of radians, do they fall in nice symmetric places on the circle that we could use? It's not very useful, right? They just kind of end up in asymmetric places relative to our axes. So we said it'd be really nice to have exactly how many radians takes us halfway around. A little bit more than 3 is what? Pi, right? That's one meaning for the number of pi. That it's how many radius lengths to get exactly halfway around. Now, based on pi, we can cut up the circle into nice symmetric pieces and get some key angles, right? How many angle measures are there, say, going around the circle? How many angle measures are there that we could have? So if I swept counterclockwise from the 3 o'clock position, how many angle measures could I define in, say, the first rotation of the circle? So that is the angle measure for a full rotation. I'm saying along the way, from 0 to 2 pi, how many angle measures could I define? Infinite, right? I can pick as many as I want. Even from 0 to 1 radian, I can pick an infinite number of angles. Okay? So as we talk about the key angles, it's important to keep in mind that we're going to focus in on what we're going to call the 16 key angles, but that's only 16 of an infinite number of angles that occur in any given arc length, okay? In any, say, one rotation. Okay? So let's talk about the 16 key angles. So the first thing we can do is we can split up the circle into equal fourths, and then again, and cut it in half. All right? So to get these angles then, so then what, if this, up at the top, what angle is that up at the top then? Half a pi, and so this one would be a half of that, which would be 1/4 pi. So to get these angles, all you need to do is count, and then we're counting in fourths. So you just count, watch, ready? So 1, 2, 3, 4, 5, 6, 7, 8 fourths. So all you have to do is count. 1, 2, 3, 4, 5, 6, 7, 8. And so now we have these 8, the first set of key angles here. So does 2 pi over 4 agree with what we know it to be, right? 2 pi over 4 is the same as pi over 2. 4 pi over 4, does it agree? Yeah, pi, halfway around. And then 1.5 pi. 8 pi over 4 is 2 pi. So when you cut up each quadrant in half, you get it by pi over 4. And so to remember them, all you have to do is just march around the circle and count. 1, 2, 3, 4, 5, 6, 7, 8. And then you can simplify the ones that we already know. We know the top is pi over 2, pi, 1.5 pi, and 2 pi. So this just gave us 4 new angles. 4 new angles. Pi over 4, half of the radian measure in the first quadrant. 3 pi over 4, half the radian measure in the second, etc. So we're splitting up the quadrants in half according to angle measure. All right, so then we can split up in terms of sit. So we can split up, turn this off. So we can split up pi into 6 instead of into 4, meaning each quadrant is split into 3 equal parts according to radian measure. And again, we're just going to count. So if this is pi, then this is 1/6 of pi. Okay, so now if we have an equal angle measure that we keep going around, we can just count. All right, we can just count. So that's 1 pi over 6. Here we go, ready? 2, 3 pi over 6, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm giving you a way that you can generate this without memorizing number for number. Okay, so it's if you've got pi over 6, then if you keep going around by pi over 6, then you just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now that gave us 2 new angles in each quadrant. We already knew that one. That's pi over 2. We already know that one. That's pi. We already know that. So now we've got 2 more new angles. Okay, and so one of those in each quadrant cannot be simplified anymore. So that's these here. Where's that? 6. So these 4 can't be simplified anymore. So these stay with 6 in the denominator. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, but the others there, 2 pi over 6 is the same as pi over 3. And this is 2 pi over 3. And this is 4 pi over 3 and 5 pi over 3. So those remaining 4 angles can be simplified into thirds. Okay? But they still come from, even though they can be simplified to thirds, they still come from by counting sixths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So let's look at the thirds. So we said we could reduce, we could change those to thirds. So that was 2, 3, 4, 5, 4 pi over 6, 8 pi over 6, 10 pi over 6. Those can be reduced to thirds, and so you get those 4 angles. So now we have, and then again, changing back the very first 4 that we knew, pi over 2, pi, 3 pi over 2, adding in the fourths. We get the 16. You're going to have to reproduce this. Okay, so I'm trying to give you a way so that there's a system you can do it without having to memorize it, number by number. Okay? And again, what was that? That was do the fourths. Those are the red ones. Just count. 1, 2, 3 pi over 4, 4, then 5 pi over 4, 6 pi over 4, 7, 8 pi over 4. So you can count around by fourths. That's the red ones. And then if you count by sixths, you get the sixths and the thirds. So 1 pi over 6, 2 pi over 6, 3, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7, 8, 9, 10, 11, 12 pi over 6. And then the ones that are the thirds can simplify to a 3 in the denominator. And then you've got, these are what we call the 16 key angles. These are the 16 key angles because they're all based on symmetry, dividing up quadrants in half and dividing up the quadrants in thirds. How many angles are there from 0 to 2 pi that we could measure? Infinite number. So sometimes students, they get so focused on these 16 key angles that they think that this is it. And so you get to a problem and there's something on a circle and it's up here. So maybe it's right here. And they say, I know, that's pi over 3. No, it's not. It's maybe close to pi over 3, but it could be something else. All right, so these aren't the only angles that exist. In fact, there's an infinitely many more. It's just that these are the ones that break up the quadrants symmetrically, okay? And we'll call those the 16 key angles. All right, so now let's talk about the sine and cosine of these. angles. So let's start with, all right, we'll start real easy here. So what's the cosine of 0? What's the cosine of 0? Yeah. And why is it 1? So why do you know that? Based on what we've been talking about.
Because the output of cosine is the x-coordinate.
Right. And it measured it.
That point is 1 and 0.
That's right. So the output of cosine is the x-coordinate, and it measures it in the fraction of the radius length. So over here, that's 1. And what's the sine of 0?
0.
Sine is vertical distance above the horizontal diameter. What is our vertical distance above the horizontal diameter when the angle is 0? 0. Piece of cake. Okay? What's the x-coordinate at the top of the circle, or for an angle of pi over 2? X-coordinate 0. Right? Or that's the value of the cosine, distance to the right of the vertical diameter. What about the sine? Y-coordinate 1. Okay, so those are easy. So does that mean that at pi over 4, which is half of an angle measure up to the top, that the sine and cosine are 0.5? So let's look at it. So I'm showing you here. Let's just turn on the... Oh, what happened? There we go. So let's just focus on at pi over 4. So let's estimate it. Come down and look here. If we take a look at the cosine, we know that's the fraction of the radius to the right of the horizontal diameter. Is it half? No. So you go halfway up the circle. You do not make it halfway horizontally. So what would you estimate it to be? Let me write these down here. This is 0.2. Yeah. So it looks like it's right real close to 0.7, halfway between 0.6 and 0.8. Okay, so we want to find that exactly. We want to find that exactly. And the way we can do that is we can look at a triangle here. So that would be our x-coordinate, agree? And that would be our y-coordinate. So I can finish this right triangle. And what do you notice about the sine of pi over 4? What does that look like it is? Same, right? It looks like it's also about 0.7. And that would make sense because we swept an angle halfway through the first quadrant. So by symmetry, it would make sense that the x and y coordinates, or the cosine and the sine, would be equal. All right? So what's the length from here to here? What's the length from there to there? 1. 1 radius length, right? And we know that if we called this, say, A, whatever the cosine is, we call it A, then the sine will be the same because we're halfway up. We're halfway up. So now we have a relationship that we can use to actually find the exact value of A, which is the cosine of pi over 4 and the sine of pi over 4. What is that relationship? How can I relate A to something so I can solve for A? Okay, so don't do any steps. Where does that come from? So start from the very beginning. Yeah, you did a step in your head, right? You did 2a squared. That's really not the very beginning. What's the very beginning? Yeah, so the Pythagorean theorem, a squared plus b squared equals c squared. But what's true about a and b here? They're the same. So we can do a squared plus a squared equals 1 squared. That's what we have in that triangle right there that corresponds to an angle of pi over 4. Now we can solve for a. We can get the cosine and the sine exactly. So this is what he said, 2a squared equals 1. Therefore, a squared equals 1/2. And how do we solve for a? Square root. Now normally we would do plus or minus, but we know these are positive values, right? So we just want the positive value. So we'll just take positive. All right, and then if we get the square root out of the denominator, this is the same as square root of 2 over 2. Okay, so if we rationalize the denominator, the square root of 1/2 is the same as the square root of 2 over 2. Okay, put it in your calculator. We expect it to be close to 0.7 in your calculator. You get 0.7, about 0.707. Which is what we see in the picture, that we're 0.7 a 0.7 fraction of the radius length to the right, and 0.7 fraction of the radius length up. Okay, so that means the coordinates of this point in fraction of a radius length are that number that we found, square root of 2 over 2, or approximately 0.707 of a radius length, up and over to the right. Okay, so now what about the other? So then we have 2 more angles in this first quadrant that we can take a look at here. So let's go to those. Okay, so first let's estimate. So for pi over 6, the angle measure of pi over 6. Okay, so the angle measure of, this is the angle measure of pi over 6 radians. So first of all, estimate the cosine and the sine of pi over 6. Just estimate, first of all. So what's an estimate? That's 1, of course. Right, so this is 0.6, 0.8, and 1 is all the way at the circle. So we want to estimate the cosine. Let's estimate the cosine. Let's do that. Matt, estimate the cosine of pi over 6. So here we are on the circle at pi over 6. And what does cosine mean? Cosine is horizontal distance to the right of the vertical diameter as a fraction of the radius length. So what would you estimate that to be for this point right here? What's that? She wants 0.85. Agree with that? As an estimate? Yeah. It's like, so here's 0.9. So that point is about 0.85 radius lengths over to the right. Good estimate, okay? So we're going to estimate 0.85. Okay? Estimate the sine of pi over 6. What does that look like? Okay, it looks like 0.5. Well, that's because I drew the tick too high. Okay, so what I'm going to tell you that the sine is exactly 0.5. That's true. So for pi over 6, I'm going to give you this information. The sine of pi over 6 is exactly 0.5. And now I want you to find the cosine exactly. Can you do it? So the sine of pi over 6 equals 0.5. That's not an estimate. Based on that and what we did before, can you find the cosine of pi over 6? See if you can do it. If you're paying attention, you can use the same kind of approach. Find the cosine of pi over 6 exactly. Who can do it? So So this is only an estimate, so we're not going to use that. We just eyeballed that. Now we're going to use some precise mathematics like we did before to figure out what the cosine of pi over 6 is. You don't need a calculator. It's not a calculator. No, a calculator is going to give you an estimate like we picked off an estimate. So we want an exact value of the cosine of pi over 6. So who is paying attention? You're going to do the same thing we did before for pi over 4. Try this one more time. Oh, yeah, there we go. All right, let's see if anyone's got it. Everyone should be working on this. You can't do it in your head. I want to see your work.
Sine and so
How do we find the cosine of pi over 4? Same way. You got the right idea? Looks like here. How do we find the cosine of pi over 4? What do we do? Yes, but you wouldn't write that equals that equation. You do like a whole colon. That doesn't equal the equation. Okay, got it. Say, did you set it up? Good. What's the length of that? Yeah. But what is it? You know what it is? The radius. Radius is what? Okay, some people are getting it. No, but that was our estimate. That's what we're trying to find. Exactly. That's the estimate. It's going to be unknown. Yeah, that's it. And then what is C? C is. It's the length. Center of the circle. What is that ultimate circle here at the center of the left? I was just thinking, distance. What's the radius from the center out to the circle? Anywhere you go. Right? Radius of the circle of 1. No. Okay, last one you got. Okay, so I told you that. Okay, we got a little bit more to do. Don't tune out, okay? I told you that was 0.5. What's the distance from here to here? It's the radius of the circle, which is 1 radius length. Again, any circle has 1 radius length. And so now if we're solving for cosine of pi over 6, that's this distance right there. So we're going to use the Pythagorean theorem again. You can call it anything you want. We'll call it a, like we did last time. So a squared plus 0.5 squared equals 1 squared. So if we do a half, keep it as fractions. All right, so when you do all the math, you should get the square root of 3 over 2, which is approximately 0.866, and we estimated 0.85, so that was a good estimate. So that exact distance is radical 3 over 2, square root of 3 over 2. But it's about 87% of the way, or 0.87 of a full radius length, to the right. So now at pi over 3, okay, so the coordinates of this point then are cosine, which is square root of 3 over 2, and sine, which is 1/2. So at pi over 3, it's the same triangle, but your legs are switched, right? By symmetry, what's the cosine of pi over 3 going to be? 1/2. What's the sine of pi over 3 going to be? Square root of 3 over 2. So let me just summarize that here. So there was our cosine and sine of pi over 6. We just find radical 3 over 2, and 1/2 is the sine, half of a radius length. We did that one already. And then at pi over 3, now your cosine's 1/2, half of a radius length, and your sine, your vertical distance, is that 0.866 number, the radical 3 over 2. So here's, now, we just found the cosine and sine of those 3 angles in the first quadrant. But really, we found the cosine and sine of all 16 key angles. Why? Because the points on the circle, by symmetry, have the same values of distance from the axes as those 3 points do. It's just a matter of applying the right positive or negative. Okay, so for instance, in the second quadrant, what would the cosine be in the second quadrant in general? Negative. So what's the cosine of 2 pi over 3? What's the cosine of 2 pi over 3? I remember. Negative 1/2. Negative 1/2. It's going to be the same distance, by symmetry, it's going to be the same distance from the vertical diameter, but this time left. It's going to be negative 1/2. What is the sine of 3 pi over 4? Positive or negative, Andrew? Why positive?
Because in the second quadrant, it's only the x value or the cosine that's
Because sine measures what?
Sine measures the vertical distance of the horizontal
Right.
diameter.
Since sine measures vertical distance, then the sine of, above the horizontal diameter, then sine of 3 pi over 4 would be equal to positive or negative radical 2 over 2. Positive, right? Okay. What about the sine or the cosine of 5 pi over 6? The cosine of 5 pi over 6. What is it? Negative square root of 3 over 2, because it's going to be the same amount away from the vertical diameter, but just left. So negative radical 3 over 2. So with symmetry and understanding the meanings for sine and cosine, as sine distance above is positive, so if it's below, it's negative. Cosine, it's distance to the right, is positive, so any distance to anything to the left of that vertical diameter will give you a negative value for the cosine. So by knowing these values in the first quadrant, we just found all the cosines and sine of all 16 key angles. Does it make sense? So let's practice. Let's try these. So I'm going to let you loose. I'll take attendance. Here it is again. Oh. Or you can pair with the person next to you, and if you need help, ask one of us. Okay, let's just do these first 6, rapid fire here. How about this Zach right here? Cosine 5 pi over 6. Okay, sine of 11 pi over 6. Bahia. Sine of 11 pi over 6. She wants negative 1/2. Valerie, cosine of 5 pi over 3. Positive 1/2. Positive, right? That's what you want. Okay. Maddie, sine of pi.
I said 0.
Okay, is it right? No. You said 0. Is it right?
Yeah.
Why?
I'm gonna stick with it. Because there's no elevation when you're at pi. If you don't go up or down, you just stay
On the
horse.
right, on the horse, you're on the horizontal diameter. So you're not any above or below it. Right. Cosine of 3 pi over 4. Sean, that's Sean.
Negative pi. Negative square root of pi. Square root of 2 over pi.
Negative square root of 2 over pi? Is that what you said?
Oh, 2.
Okay. Sine of 2 pi over 3. Odula.
I didn't get there.
Well, you can do it. Let's do it right now. Where's 2 pi over 3? Here? And the sign means what?
That's vertical.
Vertical distance above?
The horizontal. Then,
And what is that vertical distance above the horizontal diameter?
so it's half.
A half? Vertical distance is a half?
Oh,
So the vertical distance at that point on the circle is the same as the vertical distance as what other point on the circle?
the vertical.
So therefore the sign is
It's square root of 3 over 2.
square root of 3 over 2. And 2 pi over 3, is it the name of that point right there? The label?
No, it's the measure.
It's a number, right? A little bit greater than what? 3 pi is 3.14. So 3.14 over 3 times 2 would be a little greater than what? A little greater than 2, right? That's a little greater than 1 times 2. A little greater than 2. A little more than 2 radius lengths. So 2 radius lengths falls here. We're a little bit further than 2 radius lengths when we're at 2 pi over 3. Remember, all these angle measures are about their numbers. Their number of radius lengths, and therefore they're the number of radians of openness. Okay? All right, what angle measure gives a sine of 1/2? What angle measure gives a sine of 1/2? So how would we go about this? Sean?
Pi over 6 and 5 pi over 6 would be the two.
Oh, there's two?
Yes.
Is that right? Are there two answers?
Yeah.
Yeah, because when you go around the circle, so when we're on our way up, we hit 1/2 of a radius length up, and then on the way down, we hit 1/2 of a radius length up. So there's more than one answer, two answers. Is that right? It's right if what? If we restrict our angles from 0 to 2 pi. Are there more angles than just 0 to 2 pi? Are there negative angles? Are there angles greater than 2 pi? Okay, so here's how we handle that. So I want to say it's going to be at pi over 6, but also the angle measure that takes me to that same place of the circle every time I go around the circle. So I want every single angle measure that takes me to this place on the circle. Yeah, tell me.
Plus or minus 2 pi.
So plus or minus 2 pi. That can give me every single one. That'll give me two more angles, right? That'll give me if I go around once and then go there.
2 pi k.
Okay, and what's k?
Another time.
K is any integer. So now k could be 1, it could be 5, it could be 10. And I'm going to go around that many times around the circle, plus pi over 6, and that will take me to that spot of the circle and give me a sine of 1/2. Does this make sense? Is that, so what I wrote there, is that all the angles that give a sine of 1/2? Is that all the angles that give a sine of 1/2? Jacqueline, what do you think? No?
Because K is whole numbers,
Right, integers, right? Okay.
No.
So how can I finish the job? What else do I need?
You need 5 over 6 plus 2 by K.
Right. So that's going to take me always to this spot on the circle. Those are all the angle measures. They're going to always take me to that. But I also need these over here. There are, if we're allowing for angles outside of 0 to, if we restricted the angle measures from 0 to 2 pi, then yes, there are two angle measures that give a sine of 1/2. But if we allow any angle, positive or negative, and as large as we want, this is a way of expressing every single angle that will hit that spot. Okay, now you want to revise your answers to part B and C. Go. So for any angle, not just 0. So let's think both ways. So you were thinking 0 to 2 pi for B and C. Now I want you to think, now I'm going to take the restrictions off the angles. So both ways. Do it both ways. If it were 0 to 2 pi, and if it could be any angle. So what for cosine, what would we have? Let's see here. Dan. So how about from 0 to 2 pi?
From 0 to 2 pi would be 2 pi over 3 and 4 pi over 3.
Okay?
And then for it would be 2 pi over 3 plus 2 pi k. 4 pi over 3 plus 2 pi k. And the k, of course, is
Any integer. Does it make sense? So, when you have an angle, do you get exactly one? So you have an angle measure. Is there exactly one sine associated with that angle measure, or could there be more than one value of sine associated with that angle measure? Exactly one or more than one? If you're given an angle measure, exactly one value of the sine of that angle measure, or more than one? How many say exactly one? How many say more than one? Given an angle measure, here we go. I'm going to pick this angle measure right here. Is there exactly one measure of sine, or more than one? Exactly one. Given an angle measure. Given a vertical distance as a fraction of a radius length on a circle, is there exactly one angle or more than one angle? More than one angle measure that gets you. So if you're given a distance from the, say, the vertical or the horizontal diameter, that distance measure then crosses the circle twice. You get more than one angle measure that has that whatever distance you're talking about. But if you have to start with an angle measure, for any angle measure that you can pick, you only get one value of sine and one value of cosine. Okay. So normal procedure, you'll have written and web work over the weekend. See you Tuesday.